This is the Math 2 lesson summary video for the lesson titled Throwing an Interception. In Lesson 4 of Unit 5, Throwing an Interception, the purpose of this lesson is to develop the quadratic formula as a way to find the x-intercepts of a quadratic function that crosses the x-axis. We develop the formula by visualizing the distance the x-intercepts are away from the axis of symmetry. We develop the quadratic formula as this formula x equals negative b divided by 2a plus or minus the square root of b squared minus 4ac all over 2a. Another way to write that would be x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. In this lesson, we developed the quadratic formula from vertex form, which we worked with in Unit 4. We also looked at the factor form of a quadratic equation given the x-intercepts, and that form is f of x equals a times the quantity x minus p times the quantity x minus q, where p and q are the x-intercepts. Some vocabulary that is essential in this lesson is binomial, which is an algebraic expression with two terms. A trinomial, an algebraic expression consisting of three terms, and the definition of a coefficient, which is a numerical or constant quantity placed before and multiplying the variable in an algebraic expression. For example, the 4 in 4x. In this lesson, we are told that the x-intercepts of a function, f of x, is where the function f of x equals 0. We know that because when a function crosses the x-axis, our y value is always 0. In our previous unit, we discovered how to find the x-intercepts of a quadratic function by factoring. However, we can't always use factoring to help us find the x-intercepts of every parabola. That is why we need to know how to use the quadratic formula. We began this lesson by reviewing how to graph a quadratic function, which we did a lot in Unit 4. Recall that we can complete the square of a quadratic to quickly find the vertex. If we are completing the square for the equation x squared minus 2x minus 3, we will take half of b squared and we will see that we will get negative 1 squared. So to complete the square, we would have to add a 1 on the end. If you recall from Unit 4, to go from a positive 1 to a negative 3, we will have to subtract 4. Therefore, we can rewrite this equation as the quantity x minus 1 squared minus 4. From this form, recall from Unit 4 that the hk is the vertex. Therefore, the vertex in this case will be the point 1, negative 4. If you look at my graph, I've already plotted that point 1, negative 4. The equation for the line of symmetry we know is always the x value of our vertex, so x equals 1. I will sketch the axis of symmetry on the graph provided, x equals 1. Also from Unit 4, we know that if we go over 1 from the vertex and up 1 times a, we will be able to get another point on a parabola. Therefore, from the vertex, I will go over 1 and up 1, and I will get another point on the parabola. Also recall that if we go over 2 and up 4a from the vertex, so right 2 and up 4a, we will be able to get another point. So my points in blue are my parabola, and I'm going to connect them to graph my parabola by hand. So looking at number 2, we are asked what the x-intercepts are for the parabola that we've just graphed. Notice that they are negative 1, 0 and the point 3, 0. In part B, we are asked how far are the x-intercepts from the line of symmetry. If we count the units from 3, 0 to 1, we notice that there are 2 units. Likewise, from negative 1 to 1 is 2 units. Therefore, the axis of symmetry to each x-intercept is 2 units. If we always knew the line of symmetry was some line x equals h, and you know how far the x-intercepts are from the line of symmetry, for example, ours is 2 units away, how would you find the actual x-intercepts? We can take whatever that value is. Notice in our case that axis of symmetry was 1, and if we take the 1 and we add 2 to it, we should be able to get 3. So for example, in our case, h was 1. If we plug 1 in, we notice that one of our x-intercepts does check, 3, 0. Likewise, if we plug the h in, which was 1, and we subtract 2 from it, you will notice that we will get our other x-intercept, which is -1, 0. In summary, what we noticed with our examples is that the distance from the line of symmetry, in this case we'll call it d, to each of our x-intercepts should be equidistant. Again, here's an x-intercept over here, and we'll call this length d. Therefore, we can always find our x-intercepts by using these points. H minus d, which h being the x-axis of symmetry, minus the distance, 0, and h plus d, 0. So in number 3, let's think about this and use this to help us graph and find the x-intercepts for the function x squared minus 6x plus 4. We are first asked to put it in vertex form, so we will take x squared minus 6x, complete the square, half of -6 squared is 9. We will write that as a quantity squared, and we see that to go from 9 to 4, we will have to subtract 5. So this would be our vertex form. The vertex in this case would be the point 3, -5. I'm going to come to my graph, and I'm going to graph the point 3, -5. Which is here. The equation for the axis of symmetry we know will go right through the vertex. So the equation should be the point x, or the line x equals 3. So now we're asked to estimate where the x-intercepts of the function would be. Since we have noticed that the distance from the axis of symmetry, which is here, we know that our h value in this case should be 3 minus d, 0, and 3 plus d, 0. We're going to finish graphing and then estimate what d is. We know from our prior unit that we go over 1 from the vertex, up 1 times a, and same on the other side. We go over 2 from the vertex, up 4 times a. Since a is 1, I'll just go up 4. And it's symmetric. We can go over 3 from the vertex and up 9 times a. Again, a is 1, so just up 9, which will be here. Likewise, it's symmetric, so this should be my parabola graphed. Okay, now we're asked to estimate d, or the distance from each x-intercept to the axis of symmetry. So if I look at that, it looks definitely like it's over 2 whole units. So we could say approximately maybe the distance would be 2.2. And keep in mind we are estimating. I can go to the left and I see that it does look also like it's approximately 2.2. So we would say that d looks like it's approximately 2.2. In f, we are asked what the value of f of x is at the x-intercepts. Well, we know that the value of y should be 0 because we're crossing the x-axis. Therefore, we can think of this as, what if we plug 0 in where f of x is into our function, and we try to solve to get x by itself and see if that will give us the exact x-intercepts. In part G, we can algebraically solve our equation in vertex form in order to find the exact values of the x-intercepts. We would plug 0 in for f of x because we know 0 is the y value when we cross the x-axis. Our goal is to get x by itself, so we're going to add 5 to both sides first. We will get 5 equals the quantity x minus 3 squared. Mathematically, to undo a square, we have to take the square root of both sides. Those will cancel and we'll be left with the square root of 5 equals x minus 3. Now, because we took the square root of both sides, that is a plus and minus root 5. To get x by itself, we will add our 3, and we see that our x-intercepts are 3 plus or minus root 5. Now, notice in this answer that 3 was our axis of symmetry. X equals 3 was our axis of symmetry. So what our solution is telling us is that if we add root 5 to 3, we should get an x-intercept. And if we subtract root 5 from our axis of symmetry, or root 3, we should get another x-intercept. If I look at my calculator here on the left, I notice that root 5 is approximately 2.2. And that's funny because that's what we estimated when we looked at our graph. So that checks. If you look over here and we're estimating what exactly the x-intercepts are, we see that we take our axis of symmetry value, which was 3, and add the root 5, or the approximate 2.2 value, and we get that we should be crossing the x-axis at approximately 5.24 units, 0, and if we take the axis of symmetry of 3 and subtract that root 5, we should be crossing at approximately 0.76, 0. Going back to our graph to check those values, I can indeed see here in blue that this x-intercept is approximately 5.24, 0, and the other x-intercept is approximately 0.76, 0. So this confirms that our axis of symmetry will always be equidistant to each of the x-intercepts. Now in 5, we are asked to take the standard form of a quadratic function, and we are asked to put it in vertex form. We're experts at that based on our Unit 4 objectives. So if we look at our quadratic function in standard form, we know we must also take half of b and square it and add that to both sides. What we will get when we put this standard form in vertex form is the function f of x equals a times the quantity x plus b divided by 2a squared plus 4ac minus b squared over 4a. We are then asked to use that equation to write and solve to find the x-intercepts. So I'm going to bring my equation back over here in vertex form. So it was easier for me to rewrite that equation on a separate sheet. I subtracted 4ac minus b squared from both sides. Notice that the b squared will change signs when it's brought to the other side. So we can rewrite this as b squared minus 4ac divided by 4a is equal to a times the quantity x plus b divided by 2a squared. Keep in mind our goal is to get x by itself. If we multiply both sides by the reciprocal of a, we would multiply by 1 over a. That would cancel out these a's, so we would be left with b squared minus 4ac all over 4a squared would be equal to the quantity x plus b divided by 2a squared. Now again, like we did in the previous example, to get rid of a square, we would have to square root both sides. That would cancel out our square. So over here we would have x plus b divided by 2a is equal to the plus or minus the square root of b squared minus 4ac divided by, now I'm going to take the square root of 4. Square root of 4 is 2, and the square root of a squared is a. If we're trying to get x by itself, the last thing to do would be to subtract b divided by 2a. Therefore, to get x by itself, we can use the formula negative b divided by 2a plus or minus the square root of b squared minus 4ac all over 2a. Notice that this is coming from the vertex form of a quadratic function. This is what we call the quadratic formula. Moving forward, if you cannot factor to solve and find the x-intercepts of a quadratic function, you can use the quadratic formula. So let's try number 6. We're asked to find the solutions for the x-intercepts of this parabola. If we use the quadratic formula, we always need to know what our a, our b, and our c values are. Recall that the quadratic formula that we wrote on the previous page is negative b divided by 2a plus or minus the square root of b squared minus 4ac all over 2a. We're going to use this formula and plug in our a, b, and c values. Anytime we plug in, we do want to make sure that we use parentheses. So negative times negative 3 divided by 2 times 1 plus or minus the square root of negative 3 squared minus 4, a is 1, c is negative 1, and divide that whole thing by 2 times 1. I'm going to erase this so we have a little bit more space, and x will be equal to negative 3 times a negative 1 would be positive, and 2 times 1 would be 2. So this essentially is telling me that my axis of symmetry, in this case, remember the negative b over 2a, my axis of symmetry should be 3/2 if I looked at the graph. We keep going here. Let's simplify what's under the square root. We're going to have 9, and negative 4 times 1 is negative 4. Negative 4 times negative 1 is plus 4. And divide that whole thing by 2. Okay, so to write this, we can say that our x-intercepts will be 3/2 plus or minus root 5 over 2. Sometimes we might see this written as x equals 3 plus or minus root 5 over 2 instead of writing the 2 separately. But both of these answers are accurate. We would do 3 plus root 5 over 2 and 3 minus root 5 over 2. In summary, in this lesson, we learned how to apply the quadratic formula in order to find x-intercepts. We could use either one of these formulas, x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a, or x equals negative b divided by 2a plus or minus the square root of b squared minus 4ac all over 2a. Recall that in this formula, the negative b divided by the 2a will always be our axis of symmetry. And this value on the right side, which includes the square root of b squared minus 4ac divided by 2a, recall from our previous example that this value will always be our d, or the distance from the axis of symmetry to each x-intercept. If you need more help on the Ready, Set, Go homework for this task, please check the Student Support site.